pass around part of our product, and it's this tool handle, and as you get further along, we'll explain it. I'm Connor.
I'm Chase.
I'm here.
Where'd you put it?
I never.
I don't have the clicker. Camden, did you take the clicker with you?
I'll do it.
Okay, thank you.
So our initial prompt was between building and tools, and these are some of the problems that we found. The main ones being strip screws, overheating, people overheating along with their tools, wood that works, and hand-arm vibration syndrome. So here's our problem statement. We're using power tools generate significant vibrations that, if not properly managed, can lead to lasting damage to the hands and wrists. This results in a condition known as hand-arm vibration syndrome, or HAVS. Once HAVS develops, it cannot be reversed. In 2018, it was estimated that over 500,000 construction workers in the United States were at risk of developing HAVS. So one of the people we reached out to is Christine Krajnak at the CDC, and we asked her for her expertise on hand-arm vibration syndrome, and she sent us many research papers about the topic. And the main takeaways are that the exposure to vibrations from the tools can damage your DNA and cell replication, which is bad. And it depends on the frequency and amplitude of the vibrations and how long you do it, and it can also increase the risk of things such as arthritis. So we had a problem when we reached out to people. Not that many people responded to our form. I think we had a total of 4 responses across all of our forms, and it wasn't very useful data. So we weren't really able to do that.
So in our research, we found that an estimated total of 2 million construction workers are exposed to hand-arm vibration yearly. And hand-arm vibration was represented by a damage to blood vessels, nerves, muscles, and joints of the wrist and arm.
So element B had us look at existing products and identify their major successes and flaws. So one was a tool handle, which uses like gel and spring on one hand to hold the tool. But then one flaw is you're still holding the tool with one hand that's exposed to all the vibrations. And then another one was tool tape, it's a good idea, but when it comes to higher vibrations, it's not as good. As you can see, it's used for like hammers and like tennis rackets. And this uses 2 layers of elastic material, which we found when like bending around something is hard to like innovate ourselves.
So we also researched multiple different anti-vibration gloves, and we found common issues that they all seem to reduce the dexterity of fingers. That the vibration reduction was minimal at lower frequencies, and the glove padding would get worn out quickly, and they could also get stuck in tools, which would be a safety hazard. So we wanted to develop a product that can significantly decrease vibrations damaging the hands of people. The product shouldn't limit the mobility of the wearer, and it should be able to safely operate with a variety of tools, and it should cost somewhere under $50. And it should also provide a certain level of grip and heatability. So these are just some of the materials that we researched for brainstorming.
The main one that we ended up using was sorbethane, but we also looked into using rubber foams for running shoes. So here's some of the ideas that we had early on, mostly related to gloves. My idea was a glove with a strap on it, so that as you hold the tool, the strap can pull it into your wrists, and you can put a lot of extra anti-vibration material in your, just right here in your wrist, and it also reduces the strain on your finger.
I researched a lot of different like animals and how they're affected by certain vibrations, and I tried to make a glove based on the shell of a mantis shrimp.
I also went with a sort of glove idea where I had like an inner layer of padding in the glove that would help absorb some of the vibrations so they would get transmitted.
I went with a top handle for a drill. So instead of pushing force with your hand on the trigger, you could push with the top of the drill, and then that would take off force from your hand, forceful vibrations. And then the top handle would have a bunch of like vibration reduction. So then ultimately both hands are getting vibration reduction.
This is our decision matrix. So we took a lot of like those previous ideas from the last slide and a lot of other ideas, or a few other ideas that we really liked. And we talked about as a group different like elements or categories such as safety, ease of development, and like ease of testing or dexterity. And we rated these products on like which one would be the best for each category. And we decided that the two best products that we had were the Velcro strip and a vibration reduction system that would go inside of a power tool.
So some career fields we considered contacting was construction/trade workers and workers, along with physical therapists, trade teachers, power tool engineers, and manufacturers.
And sadly, not that many of them. They're really none of them except one more reached back to this.
So for element F, we took our top two ideas and kind of like looked at how they would be, like their pros or cons, their safety hazards and safety pros, and their potential life cycle. We kind of decided that working on the inside of the tool for vibration reduction would be kind of difficult to implement, and it would be really hard to check it for wear and try and replace that. And it could also cause certain like fire hazards. Whereas the outside of the tool, it would be easy to check, replace, and create into an actual prototype. And this is just the justification. We said that the outside product would be easy to control. It would significantly, or should significantly decrease vibrations coming from the tool, and should have minimal safety risks.
So this is our CAD model, and this is like the Sorba thing, and then the Velcro, and then the Velcro strip that attaches to the tool, which then attaches the Sorba thing. And you can see there's a little notch at the top, and we had to work around like the trigger. So we had that cut so that it would wrap around but not interfere with the trigger itself.
And then as we were moving into the prototyping stage, we took a look at some of the main like tools, materials, and skills that we might need. For example, we said we would need some mechanical engineering skill with soldering for testing and stuff like that. We need an accelerometer to do testing and materials like super glue or tape. And then for the actual product itself, we wanted to use Velcro, running shoe foam, rubber, and sort of thing, which is like a product that's in between rubber and foam. During building, we made a few changes as we kind of figured out what we were doing. For example, running shoe foam we found was too bulky and made the tool hard to control. Rubber also kind of, when glue was applied to it, it got really stiff and really like hard to use. And then we originally had really thick 3/8 inch sort of thing, but we sized that down to 1/8 inch to give the user more control.
So this is our final prototype. So we can see here we have our saw, and the one I passed around earlier was this front handle part. This is this front handle, and this can be directly applied using the Velcro that's wrapping around the tool, and you can directly apply it here, and then it feels nice and comfy. And then we also have that back here. So like the hook Velcro is on the attachment and like the softer side of the Velcro is on the tool. Because I feel like the hook Velcro would wear out faster.
So element H was our testing, and we needed an accelerometer, which would then hook up to that oscilloscope. And then that would measure the change in voltage, which measures the vibration. And we use this massage gun to induce the vibration.
Because our reciprocating saws, that's some shoddy reliability issues.
This is the accelerometer that was used for our testing. This allowed us to measure the vibrations because when you move a magnet, it produces electromagnetic induction. So basically it creates a current and induces a change in voltage that we could measure.
So here are all of our testing results with our product. We first used the massage gun without a handle and got that it created about 2.5 volts of electricity with the accelerometer. But when we added the handle, it only created about 2.23 volts of electricity, which when we calculated it, equated to about a 10% decrease in vibration voltage.
So we spoke to Dr. Nelson from University of Nebraska's College of Engineering for evaluation on our project, and Dr. Nelson stated that the frequency of vibration is similar to the tool that you're testing it with, such as the massage gun or reciprocating saw. You can directly compare the results with each other, so that allowed us to use the massage gun instead of our reciprocating saw to generate the vibrations.
Our final analysis and recommendations. So what would you change based on the testing? We researched that holes in the material could help reduce vibrations, but because of probably bad time utilization, we weren't able to implement that. And then be able to test different materials. We didn't have enough time to do that either. And then more extensive testing of materials used, and then test the Velcro strength.
So thank you. Do you guys have any questions?
What did you learn about time management?
We learned that we were better off trying to split up the work between us more than what we ended up doing. For example, there are parts where multiple of us were working on stuff that probably only needed one person.
And we also a lot of times I feel like we focus on certain things for too long where we should have started, at least we could have kept it in the back of our mind, but we should have started to move on, but we kept trying to do things that weren't gonna end up working.
What was your favorite part of this project?
My favorite part would be the testing, because it took us a really long time to be able to come up with how to test, and also how to formulate everything. And to finally have that come together, it felt really good.
I liked all the brainstorming processes where we got to talk to each other and bounce ideas off each other to figure out where we wanted to go.
And then I'd finally build a new thing. That was
I
the
also like having a final product.
What does a 10% reduction in vibration equate to as far as the type of challenges that people have with their wrists?
So it would reduce the chances of developing hand-arm vibration syndrome because the vibrations coming into your hand are less strong than without the material between your hand and the tool.
So would the idea for this be to, basically have strips of this available and somebody can cut it to whatever length they need, or would you make it for individual families of tools, or What's the idea?
So right now with how we currently have it set up, it's cut to be used on this particular reciprocating saw. And when we used it on our reciprocating saw, it also worked very well. So this would likely work fairly well on most reciprocating saws. Admittedly, we've only tried to. But we could, if we wanted, if to make this an actual product, we could make like a 2-foot long strip of it and sell that for like $30 and have that just be cuttable down in size.
To expand on the previous question, what is a safe level of vibration?
So you want as little as possible.
Did the professor that you talked to have any guidelines on that?
No, and it didn't seem, at least with our papers, that there's ever really like a safe level where it was like, if you need this, like you can never develop hand-arm vibration syndrome. It just seems to be a game of how much can you reduce the vibration.
Did you do any research with OSHA?
I remember we looked into it a little bit, probably not as much as we could have, but we were all over the place with our research, and just kind of compiled a bunch of different things, but we mainly focused on those CDC articles, and that was where a lot of our best research came from.
It appears that some of the OSHA stuff is based on some European standards that we weren't able to like get our hands on because they were behind very expensive paywalls. Any other questions?